Hello, I'm Sarthak Bhagat and I will be presenting the paper DisCont, Self-Supervised Visual Attribute Disentanglement using Context Vectors. This work was jointly done with Vishaal Udandarao and Shagun Uppal under the supervision of Dr. Saket, Anand. In this paper, we tackle the problem of running disentangled representations from visual data in a self-supervised manner, following Locatello et al.'s impossibility result, which stated unsupervised disentanglement is impossible without explicit inductive biases on the models and data used. We aim to exploit spatial and structural inductive biases prevalent in the visual datasets for unsupervised disentanglement. Consider an example of data possessing two attributes, that is, color and position. To this image, we apply color transformation. Only the underlying color attribute should change, but the position attribute should be preserved. Similarly, on applying a translation or a rotation to this image, the position attribute should vary, keeping the color attribute intact. So, our major contributions in this work are fourfolds, namely 1. Introducing a self-supervised multiple attribute disentanglement called DisCont. 2. Highlighting the utility of stochastic transformations in learning rich disentangled representations. 3. Presenting the idea of attribute context vectors to capture the intra-attribute variability. 4. Applying attribute clustering objective to promote disentanglement. During training, for each batch of images X, we sample a subset of augmentations and compositionally apply to X to obtain XOG and a mass vector M that contains a 0 or a 1 at each location. We construct context vectors by aggregating all the ith feature attributes locally within the sampled mini batch using the following function. Here, I will briefly go over the method. Given a batch of images, we construct an augmented batch of images using a set of positive and negative stochastic transformations. We then encode both these image batches and construct attribute context vectors from encodings of the original image batch. We then apply a set of losses both in the image space and the latent space to enforce high quality disentanglement. Coming to the various losses that we use to train DisCont. We use the standard reconstruction loss with a KL objective on the unspecified attribute. We enforce clustering among attributes using center loss by providing self-supervision in the form of pseudo-labels obtained from the context vectors. We further apply an augmentation consistency loss to ensure proximity between latent representations of the original image batch and the augmented image batch. To quantitatively evaluate our model, we use informativeness score metric. Disentangled representations need to have a low mutual information with the base data distribution, since ideally, each representation should capture at most one attribute within the data. Therefore, we expect a good disentangled representation to have a low informativeness score. We outperform state-of-the-art unsupervised disentanglement model mix on 4 benchmark datasets. We further provide qualitative evaluation in the form of latent representation visualization that clearly depict the independence of latent chunks. We also show the style transfer results for 3 datasets. On 3D shapes, the rotation and flipping augmentations help us to capture the orientation of the shapes. On cars 3D, the grayscale transformation allows us to capture the color of the car. Lastly, in sprites dataset, again, grayscale transformation helps the model to encapsulate the attribute of hair color of the caricature. For more details, please see our paper and the open source implementation on GitHub. Thank you.